Welcome to the lecture on worst case execution time estimation. The technique we are going to use is called as abstract interpretation. So, in some sense it is a very great generalization of the data flow analysis. So, you can say that this is an application of compiler techniques to execution time estimation. The difficulty is multiplied many times when there is a data cache present. People have actually done a lot when about worst case execution time estimation when there is no data cache, but only instruction cache, but in the presence of data cache the problem becomes more difficult. So, let us look at some motivation for this study. So, we are going to consider 4 sub problems apart from the introduction. So, address analysis, cache analysis, access sequencing and worst case path analysis. Then we will look at some experimental setup and conclusions. So, why is the estimation of worst case execution time of programs very important? Basically, it is important in the context of real time systems, because in the real time system scenario the correctness of the entire system depends on the computations performed and the timing of such computations. So, computations will have to be performed within a certain period of time. So, on such systems scheduling of tasks is also very important, because it is necessary to know whether the task can execute to completion within a predetermined time interval. So, because of these reasons in real time systems otherwise havoc may be created if we do not switch off a fan or a heater etcetera at a predetermined time, and that may be based on some computation which is given a deadline. So, the problem of W set estimation, we can define it as given a program and a target architecture, the W set problem is to estimate a bound on the maximum execution time taken by the program for any input data set. So, it is not the same as running the program on a given input. Here we are really trying to find the maximum execution time and a bound on it, and this should hold for any data set. So, that is the maximum we are looking at. So, what is a very simple approach to such a W set? Remember, we always want to consider the binary form of the program rather than the source form of the program, because the idiosyncrasies of the machine, that is the specialities of the machine, cannot be captured at the high level. It has to be captured only by the instruction set at the lower level. So, a very simple approach would be to assume worst case latency for every instruction. So, for example, you assume that every add instruction, perhaps when it is pipelined, floating point add may actually give you one instruction throughput every cycle when the pipeline is full, but if the pipeline is not full, then depending on the number of phases in the pipeline, say stages in the pipeline, say 3 or 4, as many cycles will be required for the instruction to complete. So, and similarly, so in that case we assume the worst case latency of 4 cycles or so for every floating point instruction. Similarly, an add instruction which fetches an operand from memory may actually take say 2 or 3 cycles if the operand is not available in the cache, but may take only 1 cycle if the operand is in the cache. So, in such a case we assume that the operand is really in memory and assume that it takes 3 cycles. So, this is the worst case scenario that we are really interested in. So, you determine the maximum execution time for each basic block and then solve an integer linear program for maximizing the execution time along any path subject to the structural constraints of the control flow graph. So, this is fairly straightforward. Once you know the branch probabilities of the execution the control flow graph, we can say what is the maximum along any path and so on and so forth. So, otherwise we can always if we do not want to take the branch probabilities, which may actually not give you W set exactly, you can take the time along every path and then take the maximum. So, that is where the integer linear program comes into picture. So, this approach may overestimate the W set by a large amount. Why? We ignore the caches, as I told you, we may ignore even the pipelining, and thereby we assume that each instruction takes the maximum amount of time, but this is not so in practice. Most of the time 97, 98, 99% of the time the cache is a hit, and once there is a there are many instructions to go through the pipeline, then the throughput through the pipeline is also going to be very good. So, in such a case the estimate is going to be much more than what it should be. So, it fails to recognize the presence of performance enhancing features such as caches and pipelines in the architecture. Now, in the context of hard real time systems, in other words there is no way you could miss a deadline, it must be satisfied in all respects. So, W set estimate of programs must be safe. So, in other words a safe estimate is one in which estimate cannot be exceeded by the actual execution time for any input data set. So, it is very similar to the safety in data flow analysis as well. Simultaneously, the estimate must be very tight to reduce the resource allocation costs. Otherwise, you would probably be allocating the resource for a much larger duration. We do not want to do that. Given the W set estimate which is very tight, we can use the resources very efficiently. So, safety may be relaxed in the case of soft real time systems, because in such a case in soft real time systems deadlines may be occasionally missed without having a significant impact on the quality of service offered. So, in such a case the W set analysis can be need not consider safety, thereby it may be violated sometimes, but most of the time it will be correct. So, what is the effect of data cache on W set? So, here is a set of programs from benchmark suites. So, by actual running on a very large number of data sets, we have computed the worst case execution time. So, this is the maximum among the data set runs that we have conducted, and assuming that all cache accesses or misses, here is the time that we have computed from the program. So, the configuration is with cache is 4 way 32 byte blocks with 256 sets, and the latencies of the cache are hit requires 1 cycle, read miss is 6 cycles, whereas write miss is 4 cycles. So, read miss is 6 because you have to fetch from memory and also write into the block and all that, whereas write miss directly writes into the memory. Now, you can easily see that the all miss value is almost twice the value of the actual simulation time. Okay. So, this is too bad, 100% excess is not acceptable. So, here is a picture, a graph which shows what is safety and what is unsafe behavior and all that. So, here is the probability of a particular time execution time taken by the program. So, here is the execution time itself. So, this is the best case execution time, and as we go along, the upper bound, that is the maximum, but too far away from the actual worst case execution time is here, and all these points are unsafe, because we get these by measurement. So, this is the reason why you cannot use measurement based execution time, you will actually be somewhere here and you will never reach this point. So, what this graph shows is some parts, some inputs actually take so much time. The maximum number of inputs probably are here, which require as much time, and there are very few inputs which really stretch the program to its worst case execution time, and that is the reason why we cannot get it easily through experimentation. Most of our inputs may be somewhere in this region. So, we will never reach this without too much effort. So, what is the existing art for W set? So, with data cache, of course, with instruction cache the analysis is simple, not too difficult, but with data cache the analysis is very hard. There are very complicated linear algebra based approaches. So, one of them uses cache miss equations, which are well known, but safe, but they do not really give you the behavior as tightly as desired. Pressburger arithmetic is another method that is used, again it has similar difficulties. Then abstract interpretation based methods use what is known as must analysis. So, must analysis says okay, what accesses must be hits, what accesses must be misses, and so on and so forth. So, this is similar to the must and may analysis in data flow analysis as well. For example, in reaching definitions, when you compute the reaching definitions, it is enough if at least one of them reaches the particular point. So, it is actually it may reach that point when it is the pointer access and so on and so forth. Even in actual execution, if the path taken is a different one, then it may not reach. So, that is why it is called a may analysis, whereas in available expressions we must make sure that the expression is available through every path at a particular point. So, it is an example of the must analysis. Then there are data flow based approaches which use a static cache simulation. So, we are not going to elaborate and then there are simulation based approaches which are measurement based. Okay. So, our approach actually will be abstract interpretation based. So, there are 4 sub problems in the worst case execution time estimation. The first one is the address analysis, which uses the abstract interpretation technique. I am going to tell you a little bit about the abstract interpretation technique as well. Then there is cache analysis, which is also abstract interpretation based. We are not going to use any cache simulators here. The third sub problem is the access sequencing problem. So, in which order should we consider the instructions and loops, etcetera, etcetera. So, here we use what is known as partial unrolling, physical and virtual. This will become clear only later. So, physical unrolling is something we all understand, unroll the loop once, twice, etcetera. But virtual unrolling implies we do not really physically unroll the loop, but we go through the analysis, goes through the loop many times, and that is what we call as virtual unrolling. Then the last one is the worst case path analysis, which uses the integer linear program formulation. The first sub problem is the address analysis problem. So, its objective is to compute a safe approximation of the set of memory locations that can be accessed by any memory reference. So, why is this essential? We are given a binary and each one of the instructions in that binary program may access a register, it may access a stack, it may access the main memory itself, it may access heap or whatever. So, there is going to be some address for each one of these locations, and we want to actually find out or rather make a safe approximation of the set of memory locations that can be accessed by any memory reference. So, if we know that it is a particular register, then we can make it concrete, there is only one reference at that point. But if we are actually accessing or if we are accessing a particular scalar variable directly, then we would be accessing a particular memory location and that would be concrete. But if we are accessing, let us say, some area in memory, some area in an array, we may not be able to say at compile time which particular element of that array is being accessed, that may not be possible. So, but we may be able to partition the array into a few parts and then say okay, this particular reference falls into this partition A, the second reference falls into partition B, etcetera, etcetera. So, the objective of address analysis is basically find out carve the entire memory space into regions for such that we know at a point in time, if we are making a memory reference, which region we are accessing. So, this is going to be very helpful for us in cache analysis as well. So, this address analysis is in general a special case of general executable analysis. There are many applications for the executable code analysis, such as detecting malicious content in code, learning about the algorithm, comparing different code versions, timing analysis that we are interested in, then cross platform porting, source code recovery and verification. So, there are many applications. It is not as if executable analysis is a specialty of our particular approach. There are many issues in address analysis. So, let us look at them in some detail. Binary code does not have type information. So, at the register level, it may be possible to say okay, this register contains integer information, this register contains floating point information and so on, because the register set may be different, but we have no information about which is a character, which is an integer, and whether this is user defined data type or whatever. So, we have no type information and it is difficult to separate address generation and address computation. So, whether the arithmetic that we are performing is on the address or it is some data is very difficult to actually separate. So, this is another issue that we have to worry about. So, compiler transformations might have changed apparent code structure. Remember, we are using binary code. So, this is already optimized code. The compiler has changed it and there is very little there may not be too much mapping, rather it may not be possible to retrieve much information from the source code and use it in the binary analysis. So, because the transformations might have changed the code structure. It is difficult to reverse map registers to source variables. We can't say which variable will be in register all the time by doing some reverse mapping. We have no information about that sort of a thing here. So, what does the traditional analysis do? So, we have used traditional analysis with some minor changes. So, basically our changes are very minor in the analysis part itself, but are major when it comes to storing the various partitions. So, there are static objects which are tracked such as registers, then statically known memory partitions such as absolute offsets, stack operations, all locations within a partition are tracked collectively. So, when we go through the program line by line or instruction by instruction, we also actually update the data structures related to the various partitions. So, there is going to be some data structures for register and for each partition as well. So, these are all going to be tracked and modified as and when necessary. So, memory partitions are determined by scanning the global data section and program code for numeric offsets and stack operations. So, this analysis gives enough information to us. We do a simultaneous numeric analysis and also pointer analysis. All computations are of course tracked, and we use actually abstractions for the computations. We will talk about these abstractions in a short while from now. So, as I said, the partitions that we get for the addresses must be stored, and in fact, when we look at the contents of these memory locations and registers, and we go through the computations that are performed in the data, we actually have to perform the same computations during our analysis of the code on the partitions as well. For example, if we say we are going to store a value in a particular register and then add something to it, we will have to actually perform this addition and then store the result again in that particular data structure corresponding to that partition. So, if we do not know the exact value, it may be a set of values, and so we will have to learn how exactly a set of values can be represented and manipulated efficiently in our mechanism. So, we define an abstract domain. So, we are going to discuss abstract interpretation in some detail now, and we define operations on the elements of that domain. So, these must be consistent with the concrete execution semantics. So, concrete execution semantics implies the actual, when we run the program, whatever is the semantics of that program in an instruction by instruction manner is called as the concrete execution semantics. So, whatever we do in abstract interpretation will be at a slightly higher or abstract level, but these must be consistent with the concrete execution semantics. In other words, you can't do addition in concrete execution semantics and multiplication in the abstract interpretation. It has to be addition all the time, but only thing is on what values do you do the addition? Is it on a set of elements or is it on a particular element, etcetera, have to be worked out properly. So, at any point in time, the set of abstract values is an over approximation of the possible set of concrete values. So, this will become clear as we go along now. So, let us take an example for abstract interpretation. So, let us consider an extremely simple language with integers and just one operation star, okay, multiplication. So, the grammar is here. An expression can be either an integer constant or of the form E star E. So, you can generate constants in this language, or you can generate expressions with star in this language. The expressions again will have integer constants in them. So, what is the concrete semantics of this small language? So, let us say the operator is rather the mapping function is mu, which takes an expression and produces a number. Okay. So, this is so when we run this program, this is what is going to happen. If there is an integer say mu of I is this stands for this int. So, it is going to be int dot value, the value of that particular integer, nothing more than that. Whereas, if it is an expression E1 star E2, then the value of that expression is mu of E1 star mu of E2. In other words, you evaluate mu the E1 with the mu function, evaluate E2 with the mu function, and then multiply the 2 in the integer domain. So, for example, if you have 15 star 6, the answer should be 90 here. So, mu of 15 star mu of 6. So, mu of 15 from here would be the value of 15, which is 15, and mu of 6 would be 6. So, the multiplication in integer domain would be 90. So, that is as far as the concrete domain is concerned. So, this is the concrete semantics and how exactly it works. So, now let us take an abstraction of this. Okay. So, what is the abstraction that we want to consider? So, let us say given an expression, the previous example could take either negative numbers or positive numbers, all integers of course, but either negative, 0 or positive, right. So, let us say we are interested in only the sign of that expression. Okay. So, here is the expression. This function sigma or the mapping function sigma will take an expression, and then it has to tell us whether it is a positive number, the result finally is positive, negative or 0. Okay. So, if you are given just an integer, sigma takes that integer. If the integer is greater than 0, then it returns plus. If the number is 0, then it gives a 0, and if the number is less than 0, it returns a minus sign. So, so far as a single integer is concerned, this is fairly straightforward. Whereas, if it is an expression E1 star E2, then again this is syntax directed. So, we apply sigma E1, we apply sigma E2, and in the abstract domain we apply this square operator, which actually here is the square operator. It tells you what the sign of the two in combination will be. So, let us take this square operator and its table. So, on this side are the three possibilities of plus, 0 and minus, and on this side we have plus, 0 and minus. So, if sigma E1 and sigma E2 are both plus, obviously the result will be plus, and the square operator also says it is plus. So far so good. If one of them is plus and the other is 0, so plus and 0 or plus and 0, the result is 0. Okay. So, plus and 0 is 0, plus and 0 is 0. So, that is obvious, because whatever we do in any multiplication, if one of the operands is 0, then the result is going to be 0. So, that is why this the result here will also be just 0. And similarly, if sigma E1 is plus and sigma E2 is minus, then the result is said to have a minus sign. This is also well known. So, if one of them is a negative operand, then multiplication, not both, one of them is negative, then the result is negative. But if both of them are negative, then the result is positive. So, this is also well known. Similarly, if one of them is 0, then again it is 0 and so on. So, in other words, sigma uses this square operator in its abstract domain, that is plus, 0 and minus in this domain, combines these two results and tells us the result of the sign of the result. So, this is the abstraction that we are looking at. So, we have actually taken integers, but then rather integer expressions, but then converted that entire thing into only, we want only the sign. So, that is the abstraction that we are looking at. So, the entire thing. So, for a single plus, there could be many integers and many expressions possible, right. So, all those are actually mapped to that plus. So, in that sense, every element of this abstract domain maps to a large number of expressions in the X domain. Okay. So, let us elaborate a bit what are abstract and concrete values. So, we know what concrete values are. So, those are our integers, right. So, we have to look at abstract values. So, let us associate each abstract value with the set of concrete values it represents. So, gamma is this function, it takes plus, minus and 0 and yields an element in the power set of z, which is the set of integers. So, in other words, as I was just now telling you, there are many integers corresponding to this plus, right, and this minus, and there is possibly one 0 with this, right, nothing more than that. So, that is what is indicated here. So, gamma of plus is all those integers which are greater than 0, gamma of 0 is just one element 0, whereas gamma of minus is all those integers which are less than 0. So, each of these is an infinite set in this case. Okay. So, very large. So, suppose we add plus this top and bottom elements to the set of abstract values, then our abstract domain becomes a lattice. Why should we do this? Lattices have very nice properties and they are easy to deal with, they are well known structures, and that is the reason we make these into a lattice. So, we can now map other operations such as plus, minus and slash to suitable operations on the abstract domain as well. So, we have considered only this simple abstraction and we considered only the star. So, we could similarly consider plus operation, minus operation, unary operation, etc., and map them appropriately to these top, bottom or plus, minus and 0 values. So, without top and bottom we will not be able to handle addition and subtraction. Okay. Forget division, that is not possible at all otherwise. So, what is a concretization function? So, we have already seen that gamma is a mapping from A at the abstract domain A to the power set of the concrete domain D. So, mapping from abstract values to sets of concrete values is done by gamma. So, that is here. Okay. This is the gamma part, and mu is our concretization function. So, we really have rather not mu is the operator which takes expressions to our concrete domain. So, mu of E is in gamma of sigma of E. Sigma of E really takes an expression to its abstract domain, and then applying gamma on it brings it back to the concrete domain. So, if you take an expression, apply mu on it, then it will be in the set of elements produced by gamma of sigma of E. Remember, gamma produces sets of elements rather than a single element. Okay. We saw that there are many integers corresponding to a single A value, that is either plus or minus or 0. So, mu really is from exp to s, whereas s is actually z. Okay. So, but here we will say yes, s is in 2 to the power d as a generalization. So, d is the concrete domain and a is the abstract domain. So, now there are other mappings also possible from 2 to the power d, that is the power set of the domain d to a, but before that the abstraction function itself. Okay. So, that is the, so here is the abstraction function which takes 2 to the d to a. So, it takes concrete values, okay, from this domain and then produces this abstraction. So, mapping from concrete values to abstract values. So, this is the dual of concretization. So, the smallest value of A, that is the abstraction of a set of concrete values. So, remember what exp does is to take this expression and produce a concrete value, or sigma does is it takes an expression and produce an abstract value, but in 2 to the power d we have sets of concrete values, right. So, what happens what the alpha does is take this set and produce an abstract value. So, that is what is indicated here 2 to the power z to a or 2 to the power d to a. So, when we map this, we will take the smallest value of a, that is the abstraction of a set of concrete values. So, it becomes clear here. So, alpha applied to this S, a set of values which is an element of 2 to the power d, it is the least upper bound, okay, lowest upper bound of minus such that the integer I is less than 0 and integer belongs to S. So, take all those elements in S, in this S which are negative, and for that minus is the representative, 0 is the representative of 0 and plus is the representative of all the positive numbers. So, we at any point in time, some may actually belong to some in a set, some of them may belong to this set, some of them may belong to this set and some may belong to this set. So, we have to take the least upper bound of these. So, taking least upper bound implies going up. Okay. So, here are some examples. If all the numbers are positive 24, 45 and 3, so they are all positive. So, the lowest smallest value of A is really plus, okay. All of them belong to this and sorry this, and there is only plus. Similarly, if all the numbers are negative, then you map, you know, the least upper bound is minus. If it is just 0, then it is a 0. In all other cases, for example, if we take a negative number and a positive number, this will map to minus and this maps to plus. So, the least upper bound minus and plus is really top. Okay. So, this is the abstraction function that we are talking about. So, what exactly is abstract interpretation? It consists of an abstract domain a concrete domain D, an abstraction function alpha and a concretization function gamma, forming what is known as a Galois connection. So, these are the elements of abstract interpretation. So, again we must have an abstract domain and a concrete domain. Okay. So, you know, we already saw examples of this. We had integers as forming a concrete domain and this plus 0 and minus forming an abstract domain, and we were mapping elements from sets of elements from concrete domain to abstract domain. So, an abstraction function alpha and a concretization function gamma. So, abstraction function takes sets of concrete elements and then gives you abstract domain element. A concretization function does the other way. It takes an element from the abstract domain and gives a set of values in the concrete domain. So, these form what is known as a Galois connection. Okay. So, I will elaborate a little more on this Galois connection very soon. So, a sound abstract semantic function sigma is also necessary and this approximates the standard semantics. So, this soundness is needed to make sure that everything is correct. So, in other words, whatever we do here, you know, should be correct. So, you can't, as I said, you can't really take a set of negative and positive numbers together and then say this abstraction function gives me negative minus or something like that. That would be unintuitive as well. So, soundness implies correctness, and this must approximate the standard semantics or the way we really want to view the entire computation. So, now we are let us look at Galois connection, which is also called as insertion. So, just to because abstract domains are very important, here is a summary. The abstract domains can be thought of as dividing the concrete domain into subsets, but these subsets are not necessarily disjoint. So, in other words, each of these concrete domain are the subsets map to a single abstract value. The abstraction function maps a subset of the concrete domain to the smallest abstract value, which I already mentioned, and the concretization function maps abstract values into sets of concrete values. So, that is what these three are, it is a summary. So, let us see what is a Galois connection. So, here is the diagram which we say must commute. So, in other words, we go like this and then take this path. So, in other words, we apply the sigma function, then the gamma function, all right. That result must be the same or consistent with the result we get when we map x to this 2 to the d directly, or we go like this and then come back and then go back, we must get the same value as we had started with, or we must at least get the value that is consistent with our intuition, okay. Or we come this way and then go back, all right, and then come down, we must still get a consistent and intuitive result. So, that is what we mean by commuting. So, this ID is the identity element. So, ID less than or equal to gamma dot alpha. So, gamma dot alpha. So, in other words, we do this once and then go back, we must actually get something consistent. So, what is that really? For all x in 2 to the d, that is in this power set of d, x is a subset of gamma of alpha of x. So, you apply, you take a subset, an element of 2 to the d, apply alpha on it, right, that is the abstract abstraction function. Then you apply gamma on it. So, you have applied alpha, got an abstract value, then you applied gamma, you would again get some concrete values. So, whatever you get, okay, so must be a subset of the x must be a subset of whatever you had got now. So, that it can't be missing some elements. So, this x must be embedded in that set that you get here when you go up and then come down again. So, that is why ID less than or equal to gamma dot alpha, whereas the other way is ID equal to alpha dot gamma. So, in other words, you apply gamma first, then you get a set of concrete values, then you apply alpha again, you must get exactly the same abstract value that you started with. So, that says for all x in 2 to the d, x equal to alpha of gamma of x. So, you apply gamma then alpha, you get you must get exactly the same element, whereas if you had applied alpha and then gamma, you would actually get a subset, okay, of what you started with. Alpha and gamma are monotonic functions. So, this goes back to what we had studied in data flow analysis. So, abstract operations of A in the abstract domain A are locally correct. So, in other words, you apply op A on A1 to An, the abstract values here, and then you apply gamma. This is a superset of the values you get when once you apply gamma on each of these A1 to An and then apply op on this in this domain. Okay. So, that is what the correctness of abstract operation in the abstract domain is. So, in other words, the abstract domain can't be something ad hoc and it can't drop elements, all these elements must be present, okay, and you can only get a subset of those when you go down, but you can't really remove everything or you can't add anything extra. Why did we do all this? As I told you, we are going to represent the various partitions as abstractions. So, because instead of a single memory location, now we have a set of memory locations. So, that set is an abstraction, and but it is not a simple set that we are looking at. For example, you may be looking at a elements separated by a value of 4. For example, you may say minus 8, minus 4, 0, 4, 8, 12, etc. And all the elements in between such as minus 3 or 2, etc. are all missing. So, we want to represent such intervals. Okay. So, it may be from minus 4 to 12, right, with the value separated by 4, a distance of 4. So, such abstractions are not easy to represent. So, we have our own method of representing them, and that is called as a circular linear progression, CLP for short. So, this is an abstraction for finite width computation. So, we have finite width in the representation of the numbers as well, number of bits is finite. And CLP, so in other words, if there is an overflow, there may be an overflow or there may be an underflow. CLPs are used to represent the discrete values contained in various static objects, namely registers, memory partitions, etc. This is what I was just now explaining. So, we provide safety on overflow, it is very handled very nicely, as we will see very soon, and the CLPs are composable. So, in other words, why is this composition important? So, we are now not adding a a concrete number like 4 to another concrete number like 5. We are really now taking two abstractions corresponding to two values, and then an instruction may actually be adding them. So, let us say a register is supposed to contain values which are separated by 4 in the range 4 to 12. Another register may contain values let us say from 3 to 15 separated by 3, and we want to add these two. Okay. The instruction may be addition of these two values. So, these are two abstractions. Now, we must know how to compose these two abstractions appropriately by the addition in this abstract domain. So, these must be defined as well. Okay. So, in other words, this abstract interpretation framework that we are going to present provides for definitions of arithmetic, logical, set, bitwise operations on these abstractions, and they are very efficient to analyze because they require only quadratic space and time for the analysis. So, this is the briefly what CLPs are about. So, what exactly is a CLP? A CLP is a 3 tuple representation. So, there is L, there is U and there is delta, and we use a finite number of bits. For example, if each of these L, U and delta require n bits, we require 3 n bits for the entire representation. L is the lower bound, U is the upper bound and the step is delta. So, in other words, if we let us take one of these minus 1, 1 and 2. So, minus 1 is the lower bound, 1 is the upper bound. So, we can visualize this entire CLP as a circle on which the values are marked. So, we have minus 1 here and plus 1 here, these are the two lower and upper bounds, and we say that 2 is the step. So, in other words, this CLP minus 1, 1 and 2 actually corresponds to the set minus 1 plus 1, that is it. It does not correspond to anything else, because these are the only two values generated by this particular abstraction of L U delta, that is minus 1, 1, 2. So, the concrete values that this particular CLP maps to are minus 1, 1, that set. Whereas, if we consider the CLP 1, minus 1 and 2, so we have 1 here and then minus 1 here and the step is 2. So, in other words, we always go in the clockwise direction. So, we would go to 3, 5, 7, etc., 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 go around that circle and then come back to this minus 1. So, there are going to be a large number of values in this particular CLP. There is a max value, max n. Okay. So, that is the maximum that you can represent using whatever number of bits that you are using to represent this abstraction. So, beyond that again the numbers are all negative. So, on this half, in this half the numbers are all positive, and in this half the numbers are all negative. So, you really can't go beyond max p for positive numbers and max n for negative numbers if it is a 2's complement representation, because you can always represent one number more in the 2's complement representation. So, there is a nice visualization possible here, see. So, you always have this circle, mark the values on the circle, travel around the circle in clockwise direction using this step. So, you go from the lower bound L to the upper bound L using delta as the step, and once you the values you accumulate in this traversal is the concrete set that you want to represent. So, that is the CLP domain and its meaning. So, let us see why this is useful. We have x equal to 3 and we also have x equal to 7. So, y equal to complement of x bit complement of course plus 4. Okay. So, this is what we want to compute. When you actually have x equal to 3 and you do y equal to tilde x plus 4, there is going to be an overflow. That is the way we have the number of bits. So, this is 3 and tilde of 3 is minus 4. So, if this was all zeros 1 1, you complement it, you get all ones and 2 zeros. So, that is nothing but minus 4 in the 2's complement notation. Then you add it to 4, you really get a 0 with this 1, right. So, there is an overflow. So, whereas if you take 7 and do tilde x plus 4, you have tilde 7 which is minus 8, add it to 4 and then you get minus 4. There is no overflow in this case. But the nice thing is the representation for y, which is minus 4 0 4, captures both these factors. Even though there is an overflow and the value is 0, we really can capture it, minus 4 and till 0. So, these are the lower bound and upper bound, and then the step is 4. So, minus 4 plus 4 is 0. So, you are capturing the two values, the set contains minus 4 and 0, it captures both these. Similarly, z is tilde y. So, when you take 0 and complement it, you get all ones, that is nothing but minus 1. So, you have minus 1 here, you have minus 4 here. So, you take a tilde on that, that is the complemented, then you get all zeros and 1 1. So, that is nothing but 3. So, minus 1 to 3 with a step of 4. So, again you get two values minus 1 and 3. So, this CLP accurately represents this computation, all these computations with both the values. So, this is not an unrealistic situation. It is possible that x comes along this path and this x comes along this path and the two values are different, and now we need to actually represent the value computed by y. That can be done using our CLP very efficiently. Otherwise, we would have been stuck with if we had used a different configuration in this case. So, we will stop this lecture at this point, and in the next lecture we will continue with other operations on the CLPs and how CLPs are used in WSET estimation. Thank you.